Hi, it's time for another math easy solution. Time to discuss further into the applied project, calculus and baseball, and now look at question 3, part C. And basically my earlier videos I went over questions 1, 2, 3 and parts A and B of question 3. And now I'm going to go over part C, but I'm not going to recap too much on this whole applied project, so make sure to watch my earlier videos on that. I basically look at the physics of baseball. Question 1 looked at the collision of baseball and bat and what kind of forces are at play there. And then question 2 looked at the amount of work needed for a pitcher to throw a 90-mile-per-hour fastball. And then question 3 looked at an outfielder fielding a ball. Well, part A looked at an outfielder collecting the ball and then throwing it all the way directly to the back catcher. And then part B looked at whether it takes less time, and then again part A looked at how much time it takes for that outfielder to throw the ball to the catcher directly. But part B looks at having the shortstop, I'll go over that position in a bit, basically having him go in between the outfielder and the catcher and then basically relaying the ball to the shortstop and then to the back catcher, as opposed to throwing it directly to the back catcher, and then basically look at whether it's shorter or faster, shorter or longer than directly throwing it. So if that back catcher, if the outfielder threw 100 feet per second or 68 miles an hour, part A looked at the time and it was 3.285. And part B, when the shortstop throws 105 feet per second, it turns out to take longer than throwing it directly. But if that shortstop could throw even faster at 115 or 78 miles an hour, and then it turns out it was slightly shorter than this 3.285, so in that case it should relay the throw. And now let's look at part C. It states, for what throwing velocity of the shortstop does a relayed throw take the same time as a direct throw? And again, to recap on what that means, basically if you had, let's say, an outfielder here, and again, outfielders are these top 3 positions. Infielders are these 4 around the bases. There's a pitcher and there's the back catcher or catcher. So let's say you had an outfielder here, collects the ball or fields the ball, whatever, however you want to say it. And then this is the shortstop is in between third and second. Let's say he runs up directly in between the catcher and the outfielder. And then basically this person throws it here. And then this person, who has a faster throw than this guy, throws it all the way to the back catcher right there. And I'll just draw that back catcher for completeness. Okay, so the idea is to compare this time and try to find the exact same time as if this outfielder threw it instead directly to the back catcher. So this relay versus direct throw. So let's just draw this out in a bit more detail. Yeah, so if we were to draw this out, let's say there's the outfielder here, and he has the ball like that, and then he throws it to the shortstop. Okay, so the shortstop collects it, and I'll just draw the bases here. So let's say that's the second base, first base, and then the third base right there, and there's the catcher, and then the catcher is right here at home plate, and then this person relays it over here. So initially the velocity of this throw is equal to, V is equal to 100 feet per second, or I'll just write FPS for short again to look at it. So the outfielder throws 100 feet per second. And then this catcher throws, this shortstop right here, this velocity as, well, that's what we're trying to find. We're trying to find what throwing velocity of the shortstop. We'll let this equal to W. Okay, so that'll be W, so V equals to W in this guy's scenario right here, and we'll call this relayed throw. So this is the relayed throw. And then basically find the time it takes that it would be the same, or what velocity to have the same as, instead they were to throw it all the way across here for a direct throw. Let's write this a bit neater. And now, again, as from part B, the total distance from here to here, the shortstop, we will let this equal to x, and then the total distance for the outfielder is as stated above. This is 280 feet. So this is just a recap on part A. So that's 280 feet. And again, let's just go up to make sure. So yeah, there's an outfielder fields the ball 280 feet away from home plate. And then the shortstop is directly in between at x, like that. And then the distance from, well, the outfielder to the shortstop, that's just 280 minus x. Yeah, so now let's write what we want from the question. So part C is asking, well, we want the velocity of the shortstop such that the time it takes for the ball to throw it in this relayed fashion. So time of relayed equals to time of a direct throw. Let's write T of direct, like that. In other words, basically I'll write this as TR equals to TD. So we want this W right here. Yeah, in other words, we're going to set these equal to each other and then solve for Y. For W. Solve for W. Okay. And now the other variable X right here, recall from part B, and we're going to use that also. We're just going to assume that X is the distance. Yeah, the distance that minimizes the relay time. Distance minimize to minimize the relay time. And again, this was from question. So from question 3, part B. So I went over that in that video, and that's what we solved as well. So we'll just show you that as well. So how far from home plate should the shortstop position himself to minimize the total time, and that's what the distance is. So this was X, and that's what we solved in part B, and I'll go over that formula in a bit as well. I'll just recap on it. So what we need to do is this again, find TR and then set it equal to TD, or the direct time. So basically what I'm going to do now is recall. So recall from question 3 part A, what I showed was basically TD, the direct throw, was just 3.285 seconds. So we've already solved this in question 3A. That's a direct throw, and there's the answer there as well, 3.285, and that's for the direct throw. So we have that, and now what we're going to do is recall. So we've already solved for TD, is just 3.285. Now recall from question 3 part B. Now we're going to get into the more complicated parts. So the distance X to minimize the time, the relay time, is equal to 5W minus 360. And W is the speed of the shortstop's throw. And now also recall from question 3 part B that the relay time is a function of X, and this equals 2 1/2 minus 10 times, and now this is going to be ln of 720, this was plus X minus 1000, this is going to be plus, not minus, so plus ln of 10W minus X over 10 times W. So it's just a big formula like that. And again, make sure to watch my question 3 part B to see the derivation of this. So now that we have these values, so what we need to do is basically set, because we're going to use the X value as the one to minimize TR, and that is this one right here, 5W minus 360. So what we're going to do is set TR of 5W minus 360 equals to TD, and then solve for that W inside, and this equals 3.285 seconds. So let's just plug this inside this big formula. So we get TR 5W minus 360 is equal to 1/2 minus 10 times ln of, now we have 720 minus, there's a plus, not minus, 5W minus 360 and then this is all divided by 1,000. Let's get a better bracket right here. And then plus, let's move it here to save some space. Now this is 10W, so we have ln of 10W minus x, which is 5W minus 360, all divided by, this is 10W, all big bracket like that, and then square bracket. So that is what we have. Now we could simplify this further. Yeah, by just 720 minus 360, well, that's just, 360 is just half of 720. So that's just 360. So this would be equal to 1/2 minus 10, and then ln of, this is 5W plus 360, 720 minus 360 is just 360. Okay, so now we have this. And then we add this one here, so 10W minus 5W, that is just 5W. Write a bigger bracket. And then we have the subtraction of negative 360, that just becomes positive 360, and then this 10W is like that. Okay. And now, just to simplify this even further, we're going to recall the logarithmic property, and you can see that in my earlier videos. I'll put that in the video link below. Basically, ln, whenever you have ln of A plus, let's say, ln of B, this equals to, or log base of this, the same base for the logarithm, this equals to a multiplication of the A and B. So this equals ln A times B. Yeah, so basically we could simplify this, and you can see the derivation again in the video link below. So what we have now is this just equals to this thing. We can simplify it for the 1/2. This is minus 10, and then ln, now these are combined, the 2. And then when we combine these two, notice on the top, actually we're going to remove this bracket because it's combined into one logarithm, so we'll put the bracket here. Now this 5W plus 360, and this is 5W plus 360, just multiplied that by each other, or actually I'll just do that afterwards. 360, actually yeah, we'll just square it. So that when you have it multiplied, that's just squared, and then the bottom, what we have is this 1,000 times it by this, well, 10W, let's leave it like that. And now before I get further, I just want to simplify the top, because we could factor out this 5W. So we have this 5W plus 360, or actually I'll just put that whole thing in here. So 5W plus 360 squared, and then this equals to, actually, yeah, let's put this here as well. So 1,000 times 10W, and then this one here we could simplify this further. So the 5, we could factor it out by writing, well, 5 times, just take that out. So we have 5W plus, and then this one is, well, 360. Let's put it here in the bracket. So 360 divided by 5. That is, well, 5 goes into here, 35. So that's 7 times. Subtract, we have a 1. Bring this down, 0. 5 goes in here twice. So we have this 72, and then this is bracket squared. So we just took the 5 out. There is a 1,000 here times 10W. And now what we end up having here is this 5 squared, and then times it by, let's put this in another bracket like that. And then so the 5 squared is over there, plus 72 squared, and then to put this 1,000 there. 5 squared is just 25. So I'll just erase that. So that's just 25. And now this 25 goes into 1,000. I'll cancel that. This goes to 1. And it goes into 1,000, well, just 40 times. Because remember, 4 times 25 is 100. This is 1,000, so add another 0. So we have 400 times 10. So this equals to W plus 72 squared over 400W. So now that we've simplified that, we could plug that back into this formula. And then what we end up getting is, drag this down, T of the relayed time, or the relayed throw of 5W of, this is the minimized distance, 360, equals 2, and then we have 1/2 minus 10 ln, and then in bracket, I'll put a square bracket, W plus 72 squared, and then this whole thing just becomes this right here, divided by 400W. Erase this. 400W. So this is now our formula for the relay time at the minimized distance, 5W minus 360. Now this is a very complicated one, complicated formula. It's not too easy to just solve for W specifically, or explicitly, I mean. So what we'll do is graph it instead and then solve for it graphically, and I'll go over that in a bit. But basically what we want is set TR 5W minus, again I already wrote this down above, equals 2 TD equals 3.285. So it's not easy to solve for W, or I'm not even sure if it's possible. So we set it equal to this and then solve for W. Alright, so now if you graph this out here, I use Google's graphing calculator. Instead of W, put X, because for some reason W doesn't work in their calculator. So it graphs it out just so whenever it says X, that's W, and whenever it says Y, that's just our time, or relay time. So we have this graph right here. I graphed that function 1/2 minus 10 ln x plus 72 squared divided by 400 times x. And then also the y equals, or the time, direct throw time, 3.285, and show it crosses it like that. So we have something like looks like this, and I'll explain why it crosses it twice. And basically we got to solve for when it's equal, and that's this or this, but it's actually this value right here. So here I copied and pasted that formula here, and again this is our time. This y is actually TD. I'll put time like that. And then this right here is T direct throw is 3.285 seconds. And then this axis, this is our W. So that's our W right there. This is our time axis. And then whenever it says X, that's actually W. This is W. I just couldn't put W for some reason in the graphing calculator, and Google doesn't work. So what we have here is, well, two values here or here, but what we have to do is note that the domain of X, well, X, which is the distance from the shortstop to the home plate, so remember X is distance from here to here, so it has to be, well, obviously greater than 0 and also less than 280 feet, because you can't be, there's no point of this person throwing it behind himself, which just doesn't make any sense. So well, actually, technically, it could make sense if he was behind himself and he threw, let's say, really, really fast, and then it would make sense. But it just doesn't make any sense in real life, because no way he's going to run all the way behind him while he's catching it just to get the ball and then throw it again. But anyway, so ignore that part. So it's, ignore that part. It's not practical. So what we'll look at is, well, X is less than 280 feet, because otherwise he'll be in front of the outfielder, and it's greater than or equal to 0, because otherwise there's no point of throwing it to him, just throw it to the catcher. So this is in between these two right here, and we also know that our X is our minimized distance to minimize the relay time, which was just 5W minus 360. So we have 0, let's put that in here. And then this is going to be less than or equal to 280. And now what we'll do is just, add 360 on all the sides just to get a W value. What we're trying to do is find the domain of W that actually matters. And then add 360 on this side. So we're doing it on every single side, so we're not changing anything. So what we have is finally here 360 less than or equal to 5W, and then this part here, this is less than or equal to, well, this just becomes 0, and then 6 plus 8 is 14, carry the 1, and then we have, that's, what is that again, 14, carry the 1, 3 plus 2 is 5, plus 1 is 640. And then divide everything by 5 to get rid of it like that. So we have this, and again, if you want to learn more about addition by hand, just look at my earlier videos on that if you haven't already, and I'll put that in the link below. So now also we have this right here, so 5 divided by goes into 360. Well, let's just do that by hand right here. This is 360 360 goes into 5. Well, that's, oh, we already saw this one above. That's just 7 times. Goes to 35. Minus from it, we have 1. Carry the zeros, 72. And this part right here, 640 divided by 5. Well, 5 goes into it once. 5 times 1 is 5. Minus, so we have 1. Put the 4 down. 5 goes into it. Well, yeah, and basically 5 goes into 14, well, twice. That's just 10. Subtract this down, we get, well, 4. Put this down right here, and now 5 goes into 40, well, 8 times. So we have 72, and this is 108. So bring this down, and now we finally have 72 less than W and less than, and I'll put this actually in feet per second. 72 feet per second. Write this neater. Okay. And then W is less than equal to, well, 128 feet per second. Yeah, actually I just removed that feet per second. Didn't look too nice there. Just leave it over here. So basically W is between 72 and 128 feet per second. Like that. I'll highlight this. So that is the domain of the W. So what that means is, well, first of all, yeah, what this means at 72, that is basically 72 feet per second. The minimum distance would be, well, 0. So, yeah, so whereas just at the back catcher, which doesn't, yeah, it's not practical. So when you increase it further, the speed obviously is going to have to drop because your distance is going to go away. So that means, well, again, if you were to look at it right here, this 50, the 72 is actually somewhere around there. So there's 6, 7, and roughly here, about 72, which is about this peak, which is exactly actually at that peak. And then when we go over to 128 feet per second, that's, well, 2. And then there is the, I mean, this is 110, 120, so 102 is about here. This is 130, so it's about here. And if I go up like this, that's actually somewhere around there. And this is 128 right there. So what that means is it's in between somewhere here and here. So the only graph we're going to look at, or the only point, is this one here. If it's anywhere here, that means that you're, well, behind the behind the catcher, which just doesn't make any sense. So this is the only part of the graph that's applicable. So what we need to do is find this point right across here, and that should be about 1, 1, and then something in between there. So what we'll do is, well, what I did is I zoomed in. So here is that same graph. I just went and zoomed in all the way, and that same thing. So we have 3.285 all the way to here, and it's about 112.8, and then if you look at it on this side, 112.81-ish, and yeah, and here I've copied and pasted that right here, and as you can see, it's yeah, about that point, about 112.82 or 81-ish. It's a bit off it, but we're just going to do is round it up to this value right here. So this is about, what we'll do is write, yeah, W is roughly equal to 112.8 feet per second. So what this means is basically or instead actually we'll write thus, the relay time TR is equal to the direct throw time TD if the shortstop velocity is roughly equal to 112.8 feet per second, like that. And then in miles an hour, just to get a perspective, that is about, here's plugging the Google calculator, 112.8 to miles an hour. This is 76.9. So this is about, I'll just round it up to 77 miles an hour. Yeah, and also for completeness, I just wanted to plug in that 112.8 inside that big formula of the relay time at the minimized distance x. When you plug in 112.8, it's plus 72 squared, 400 times 112.8, that's our W. we get 3.285, which is, and then etc., because we rounded up. So this is the time of the direct throw, which is correct. Yeah, and also one more thing is basically here, if you were to look at what that distance of the shortstop is from the back catcher, so plug in our X formula, 5W minus 360, so put in 112.8, so we get about 204. So in this case we have X, which equals to 5W minus 360, roughly equal to 5112.8. And then this is going to be, let's erase this, feet per second, and this is roughly equal to 204 feet from the backcatcher, as opposed to the 180 total feet the outfielder is. Anyways, that is all for today. If you learned from this pretty extensive example question of both part C of question 3. And that's the conclusion of this applied project, which I've went over in my other videos, which is pretty in depth and goes over to the physics of calculus, which is quite complex for even such basic things as relay throw or direct throw. So basically, again, to recap part C, if the shortstop goes about 204 feet away and throws it about 77 miles an hour or 112.8 feet per second, then he would throw it, the total time from the outfielder to him all the way to the catcher would be the same as a direct throw. So in that case, the manager could choose to throw or not, doesn't matter. I would just, in that case, I would stick with a direct throw because less chance of error. Anyways, it's all for today. If you learned, and make sure to check this applied project out. It's pretty interesting to see just the amount of force it takes to hit the ball, as well as to throw a fastball, etc. Anyways, it's all for today. If you learned, like always, you could download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.